Okay, so this is a video to show you how to get an equation of motion for an object with a constant acceleration. In this case, that acceleration is due to the gravitational force. We haven't really talked about that yet, but that's cool. Let me just get into it, and then we'll be all together. It's gonna be great. Okay, so here's the situation. I have some ball that's launched with some initial velocity vector v0 at the ground, and it flies through the air, and then it lands over here, and I want to find out where this is, the position r at any time, and I can do that. So let me start off with a couple definitions. Number one, I have this one. This is the definition of the average velocity vector. So this says the average velocity over any time interval is the change in the r position divided by the change in time, however long that took. Okay, we got that. Now we also have the definition of acceleration. The velocity tells you how your position changes. Acceleration tells you how your velocity changes. So it looks very similar. It's the change in velocity over the change in time, and so the change in position over the change in time. Now I don't have an average here because if the acceleration is constant, then the acceleration at the beginning as the end as the average are all the same. So you don't need to put that. And that's what we're dealing with here. So in this particular case for projectile motion, it turns out that the acceleration is equal to the vector g. And g is the gravitational field. It has a value of 0, negative 9.8, 0 newtons per kilogram on the surface of the Earth. Now, it turns out that this gives it an acceleration of 0, negative 9.8, 0 meters per second squared. But we'll talk about the connection between mass and acceleration and forces later. Now we just want to say it has an acceleration g. So let me start up here with the acceleration g. I'm just going to call it a for right now. Okay. So a is the change in velocity or the change in time. If I take a time interval starting from, let's say, v0 to some other time here, I'll call it v1. It goes from 0 to 1. Then what would the change in velocity be? So I can write this as a equals v1 minus v0 over delta t, where delta t is going to be t1 minus t0, but I'm going to leave it as delta t. Okay, so that's just the definition of change in, right? If I go from here to there, the change in velocity is the final, which is v1, minus initial, which is v0. I can multiply both sides by delta t, and I get v1 minus v0 equals a delta t. I'm trying to think where I was going here. That's fine. So now I'm going to solve for v1. v1 equals v0. I add v0 to both sides. v0 plus a times delta t. Okay, great. But I really care about the position. So let me do the same thing up here with the position. So if I write v average as r1 minus r0 over the change in time, I can do this. It looks the same thing, so I'm going to solve it the same way. And I get r1 equals r0 plus v average delta t. And that's a vector. Be very careful with the vectors, right? Here I have a vector on the left side of the equation. The right side has to be a vector. So this is a vector. That's a vector times a scalar, which is equal to a vector. Okay, you can't have vector times a vector. You cannot have a vector equal to a scalar. So that's where I'm right there. Now, but I don't know the average velocity. But I can write average velocity, v average, is equal to v1 plus v0 over 2. I can literally just average them. Because the acceleration is constant, I can just add the final and the initial and divide by 2. So I'm going to put that in right here. So I get r1 equals r0 plus v1 plus v0 over 2 delta t. Now I can take this expression for v1 and put it in down here. So now I get, move my paper up a little bit, r1 equals r0 plus v1. I'm going to put all this stuff right there. So I have a 1/2. I'm going to say 1/2 times v1, which is v0 plus a delta t plus v0 vector times delta t. All I did was substitute in v1 right there. Now I can write this as r1 equals r0. I get I have two v0s. So I get 2v0, add these together, and then I can multiply this by a half. So I'll write that out as plus 2v0 over 2, and then I have a delta t. And then I have 1/2 times a times delta t times another delta t. So I get plus 1/2 a delta t quantity squared. So this just becomes, and in fact, this could work for any final position. It doesn't really matter where I go. I could say r as a function of time is equal to the starting position plus 2 over 2 is 1, so this is v0 delta t, plus, I'm going to change this a to g, 1/2 g delta t squared. And now if I call this t equals 0 as the first time at 0 seconds, then I could replace delta t with just t. But this is the equation of motion. So all I'll do is, because look, I can put in any final time or the change in time. I know the gravitational field, g. I know the initial velocity. I know the initial position. I can find any position. So this solves the whole thing. I can find out where it is at any time and do whatever I want. I have mastered and dominated this particular situation. I know everything there is. It's like the power word, right, for that. I know it all. There you go. That's projectile motion.